Okay, let me make you the boss. Come on, machine, quit being a snot. There you go.
Okay.
You and boss, the recorder is running. I'm going to stop my video and I'll mute. I'll be listening in, but I'll be distracted.
Okay. Let's see. Can everyone see my screen and also hear me? Oh, looks like they were expecting that. Good. Okay, so before we get into the actual lab, we're going to go through an example of testing hypothesis in that's from the lesson. So as you can see, here's the link to it. The important thing to remember in almost everything, at least, I'll say this in a scientific sense. So important thing to remember in a scientific sense is really what is your input and what is your output. That's extremely important. You hear me harp on it a lot, but it helps you not get confused because, amongst other things, when you know how many and what kind of things are your input, you can make sure you have them. And you know what kind of thing and how many there are as your output, you can gauge whether what you're doing is correct or not pretty easily, instead of just running it and it's like, okay, I got an output, it's good enough. So in this example, we need to make sure we have a null hypothesis and an alternative hypothesis. So what kind of thing can be a null hypothesis? Anything that can be verified or falsified. So something has to either be true or not true. We can't have something that has 3 values or assigning a numerical value. We have to have something like the coin I have in my hand is fair or not. So the coin I have in my hand could be our null hypothesis. And the coin I have in my hand is not fair is the alternative hypothesis. Next thing we need is a test statistic. So I'm going to flip the coin 1,000 times and count how many times there's heads and how many times there's tails. And we also need a rejection region. So what's that? Well, we have our test statistic of recorded data. Every single point on this curve is an experiment I did. So I flipped the coin 1,000 times and I recorded how many times it was, let's say, heads. So right here is 500. And so this is our statistic, and the rejection region is going to be something like this stuff here and this stuff here. We're saying it's not exactly the case that only an unfair coin can possibly flip this many tails, so like 300 heads or 700 heads, but it is extremely unlikely. Extremely unlikely. So this is our rejection region. Okay. So with those 4 things in mind, let's do an example. We have a machine in a factory that has to be stopped and maintained when its defects exceed 10% on the daily production run. Okay. A random sample of 100 items from one day of production contain 15 defective items, and the shop foreman claims the machine must be maintained and repaired. Does the sample evidence support the forum's assertion? Let's apply our process. So we have a random variable y. And we're going to say it denotes the number of defective widgets. Every time I do this example, I say it's a widget factory. The machine makes widgets. So y will be a binomial variate with value true or false. It's got a probability of one outcome of p and the other of 1 minus p. Kind of like a coin that is weighted. Let's say the defect outcome is the value p. We will assume 100 is large enough so that we can approximate the binomial with a z-score statistic. Choosing the right sample size, I won't say it's difficult once you actually know the rules of it, but when you don't, it can be difficult. Just know that choosing the sample size is important. But we have this wonderful thing called an assumption. We're assuming that it's safe to assume that 100 is large enough. Cool. So we don't have to worry about it anymore. All right. So our null hypothesis is that the defect likelihood is going to be 10%. The place we reject the null hypothesis will be the defect likelihood being greater than 10%. Our test statistic is the normal one. This is the formula from up above, where p is our likelihood. So we have the mean minus the one we're looking at over the square root of the one we're looking at times 1 minus that over n. Not super important, you know the derivation of these formula. And our rejection region is going to be that z is greater than some z alpha for some value alpha. We're going to say let alpha be 0.01. So now the question is, what is z alpha? That's where we know when our rejection region is. Well, we could do it all by hand, but we have code. So let's do that. All right, so what do we have here? We're going to define our normal distribution as follows. It takes 3 arguments. It takes x, takes mu, and sigma. What's x? It's our input. What's mu? That's going to be the mean, and sigma is the standard deviation, I think. Yeah. All right. So we're going to calculate this variable called argument using the formula we just showed, the one here. And then from there, we're going to take our normal distribution with that argument and return it. So we have a sample size of 100. We've recorded that there's 15 defects. We want to get the ratio, defect count over sample count, and then we can calculate our z-test from there. So let's go ahead and run this and see what happens. Well, before I run it, let's see what the output is going to possibly be. If our z-test is greater than our z alpha, we're going to say the following. So we reject the null hypothesis. Otherwise, we don't reject it. Now we can try a couple different z alphas just to see what happens. But let's go ahead. All right, so with a z alpha of 2.325, we do not reject the null hypothesis. The likelihood that we made a type 1 error is 0.01. And we would have rejected at 0.04. Let's see what happens when we change this to 1.6 instead. Well, if we set z alpha to be 1.64, we do reject. So had we chosen that instead, we would have gotten a different value. Here with the original 2.32, we don't reject. And we can visualize this. And I'll visualize the not rejecting first. Here we have the histogram. We've got what, 9 bins? Okay. And remember where we set our rejection to be. So 2.32, and we're well under that. But if we set it to, what was it? 1.6. We can see we have, or sorry, 0.16, more in that bin than is acceptable. Okay. So that's the quick little example of applying the process of our z-test. We have an A/B test example in the lab, so I'm not going to go through this. In fact, I think it's actually this one. Yeah, it is. Okay, any questions before I move on to the actual scheduled regular program? All this is in the lesson. You can just copy and paste it into a notebook and it'll work just fine. That's what I did. If you're taking this class, that means you're in the College of Engineering. So eventually you're going to have a statistics class. Most of you will be taking statistics for engineers. So when asked about this, I say there's 2 statistic classes. One is for people who are generally a math major, and one is, it's the one I took. And the one is for people who aren't math major. The big difference is the one that's not for math majors. Here's the attitude of the entire class. Here's the test statistic. I don't need to know how it came into be. I just need to know how to use it. That's the general attitude. So you're going to be given a lot of tools. You're going to be shown where to use them, how to use them, and what they can be used for. But you don't need to derive them or figure out how they work. The math version of statistics is, yeah, you're going to have to derive everything. So the reason to bring this up is if you're sitting here confused, like, man, I don't understand how this formula, why is it this way? Well, depending on your major, I would tell you don't worry about it. Just know how you can use it and when are the acceptable times to use it. All right. Since I didn't get any questions, let's go do some more statistics. All right, we're going to be talking about confidence intervals today. And the example we're going to use is here. How many people love soccer? So for the first example, we're going to look at a problem from 2 perspectives, or 2 modes, if you may. What this involves is, do you have total knowledge of your sample population or not? So you can view the God mode, the God perspective, as having total knowledge of your entire population. You can liken this to having in literature, there's a couple different perspectives. There's like first person perspective, third person perspective. This is the omniscient perspective. This is where you as the observer know everything. So you can actually get the pure value of all the variables. So in this instance, you know every gravitational constant, everything about the universe. And this is useful to talk about in theory so that we can understand the true nature of things. But we as people living in the physical universe, we can't actually know the raw details of everything. We can't look behind the curtain to see what all the gravitational constants are and every particle and all that fun stuff. We just know that they're there, and let's assume that we can know them in this mode, but we don't actually get to know them in real life. Okay, so let's go from the perspective that we know everything first. Suppose, theoretically, we know the exact percentage of people in Italy that love soccer, and it's 75%. 75% of all people in Italy love soccer. So let's say we want to know the chance of randomly selecting a group of 1,000 people that only 73% of them love soccer. So what do we know so far? Of the people in Italy, which is, we'll say 60 million, we know 75% of them love soccer. So what's the likelihood that I randomly select 1,000 and only 73% of those people love soccer, which would, that's not the actual percentage of the entire population. So we've got the total population. We've got the ratio of those people who love soccer. And here we have I'm sorry, if I said population, I meant to say the percentage. And here we would have the actual number of people who love it. And here would be the population who don't. So the population of everybody who loves soccer plus the population of everybody who doesn't love soccer should be everybody, because we're not allowing any fence sitters. Okay, we've got all that. Let's create an array. I think I need to clear all these. Let's create an array with 60 million elements, with a 1 for each person who loves soccer and 0 otherwise. So we're making a NumPy array for every person in Italy. Every person is going to be assigned a 1 or a 0. 1 if you love soccer and 0 if you don't. Okay, so I've got my array of 1s and I've got my array of 0s. And how do I know how many to put in there? Well, remember I have the population of lovers and the population of non-lovers. So I'm going to use those, and then I'm going to smush them together into one big array. Okay, I've got those. Well, let's print out the mean of what we got here to make sure that it actually exists and it's got the right amount of people. Well, of our entire, let's see, I think I can do this. I'm not going to print the whole thing. This would be a mistake because it's 60 million lines long, but I think, let's try this. Maybe this. No, it doesn't have a describe. Oh, well. I'll try one more thing. Nope. Size takes an argument. I don't remember what it is. I could look it up, but I don't want to take the 60 seconds that it would require. But I can get the mean. And now what we're going to do is we're going to randomly sample from our NumPy array. Now, what is our NumPy array? I don't know. Somebody tell me. What is it? What's its size? And what does it contain? Oh, wait. Of course I did that wrong. I should have done this. There we go. So I've given you half the answer. What kind of thing is this? What I have highlighted here, total population. What is it? It's an array of length 60 million full of 1s and 0s. Yes. The only thing I would say is that it's not an array. It is a NumPy array, but close enough. They slightly different, but I know what you mean. Okay. So we've gotten our array, 60 million long, and it's got 0s and 1s in there, and we don't care about the order. I'm pretty sure the order is just going to be all the 0s and then all the 1s. Now, how's that going to work? We want to randomly do stuff, right? Well, we have the ability to randomly select from something, so that's what we're going to do. So a single sample is going to be from my array of 60 million. I'm going to take 1,000. That's a single sample. So let's take one. What's my ratio of football lovers? Well, this one has 76.6%. Okay, that's pretty close to 75. Let's do it again. 73.2, 73.7, 77.3. So every single time I run this, that's a sample. Okay, well, that's nice. We want to take a bunch of samples. Why do I want to do that? Because I want to, well, here's the question we're trying to answer. What's the likelihood of getting a 73% out of taking a sample? Well, how many times do I have to run this in order to tell you that? How many times do I need to take a sample before I can, with absolute certainty, answer the question of what's the likelihood of getting a 73? So to simplify that a little bit, let's say I'm trying to determine whether a coin is fair or not. And we're not talking about degrees of certainty. I mean, to know with absolute truth whether a coin is fair or not, how many times do I have to flip it? Yeah, I would have accepted you can't know that. Those are both correct. That is technically correct, which is the best kind of correct, at least two. You would have to flip the coin an infinite number of times, which we can't do. But what we can do is I can say, I'll take 10 samples and this will give me some data and it'll give me a degree of certainty. So I have sample 0, sample 9, blah, 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 all the way through. Okay. I can keep doing this forever and ever. But I can't actually, because I have a finite lifespan. But we know from some math stuff that as we continue to do this for a long amount of time, the average should tend towards 75. And so if we consider the coin, if I flip it forever better than that, if I say I have a machine, let's say I have a machine that flips the coin, simulates flipping the coin, doesn't actually physically do it. It does it, the computer does it. If I tell it to do it for a large enough sample, that it should tend towards 50-50 if it's fair coin. Same thing here. So we're going to say 10,000 times, do a sample. So 10,000 times, choose 1,000 people and get the ratio. And then what I want you to do is take all those ratios and average them together and tell me what it looks like. So let's do that. So we have the mean of all of these ratios. 10,000 times I did it. And then I also have the standard deviation for those 10,000 ratios. Okay. So I did it 10,000 times. Is that absolute certainty? No, it's not. Here's an easy way to know how it's not. I could always do it 100,000 times and I would be more sure. I hope this still works. And I'm going to do it 100,000 times. Is this absolute certainty? No. Why? Because I can be more sure. Just add another 0. How many zeros can I add? Well, my machine has a physical amount of memory, so eventually it'll run out. But theoretically, I could just keep adding zeros forever and ever. So we're going to never actually be as sure as the God perspective. But 74.996 is pretty close. Let's plot a histogram to visualize some of this. Now, I added 2 extra zeros here, so maybe, well, we'll see what happens. Okay, so again, these are just warnings, so don't worry about them. What we see here, even though there are these spikes, you can still see that the average which will be the line here, conforms around the 75%, which is what we expected. And I can run this again and it'll look slightly different. Takes a little bit because I put 2 extra zeros in there. Still going. Maybe I added another one when I wasn't looking. All right, I'm going to take one out. Let's see, the one we started with was 10,000. So let's do that. Okay. There we go. I can run it again. And again. And even though the there are these, I won't call them outliers because outliers are to their left and right, but these spikes, you can see they're still symmetrical. So take that whole process, the one every time I run this. So I'm going to run this and then visualize it. So that's the process. So take that process and let's do that a very large number of times. Let's say infinite. If we do that forever, we're going to get a histogram that's almost identical to the normal distribution. So let's try it. I think this is exactly what I was just doing. That's a bunch. All right, let's see what happens. While that's running, anybody got any questions, comments, concerns, or good jokes? Or bad jokes? Still going. Let's see, this is 1 million, right? Yeah, coming up with jokes on the spot is tough. Believe me, I know. So we started with 10,000 and we're up to 1 million. So we'll, oh, it's done. All right, so instead of 74.99, we have 74.999. Let's see what it looks like when we make a histogram. Warnings, warnings. Okay. As we can see, the thing we're really interested in is the line. When I run the smaller sample, we get the line. It's kind of lumpy, but mostly normal looking. And by that, I mean, looks like the normal distribution, kind of. This one looks almost exactly like the normal distribution. Okay, so we are approaching the true nature of our supposed population. So we can finally get to the point to where we can begin to answer our question. We can see here from our box plot that the mean is what we said it was. And we can see where the quartiles are of, if we take a random sample of 1,000, what we would expect to see. And the original question was 73%, I believe. And that's kind of down here. So what's the likelihood going to be down there? So finally, we can get to the point where we can ask, how can I take an infinite number of samples and does it help you? Well, the answer to the first one is if you aren't omniscient, if you're not God, then no, you can't. The universe has a finite number of amount of time in it. You can't, unless you're in the business of creating universes, then you can't take an infinite number of samples. Well, even if we could, would it be nice to be able to? Well, let's find out. We initially took 1,000 people and got close to 75, but not exactly. We wanted to know what's the random chance that we'll get 73. Using the information above, we can say that there's about a 20% chance. We don't actually need to do an infinite number of samples. In other words, the man mode's good enough. And here we'll show why. So using the fact that we don't have total knowledge, we can get the actual percentage pretty close. In fact, we can do the same thing without knowing anything about the population. We do know one thing. We just took a sample and we got 73%. How does that help? Well, you may recall a couple times I've mentioned what's visualized here. If you have a normal distribution with the mean right here, you can go a standard deviation to either side of the mean, and that will get you a certain chunk of your population. So if I go one standard deviation in either way, this is a certain chunk of the population. Well, how much? Is it 50%? Is it 90%? Well, I know that this this chunk right here has more above this line than here. So this is missing everything here and everything here. So I know that there's more stuff here than there is here. So what does that get me? That gets me that if I go one standard deviation in either way, I'm going to get most of my population, at least 50%. The actual number is 68%. So if I go one standard deviation in either way, I'm going to get 68% of my population. What the heck does that mean? It means if I have my population where 75% of people like soccer, then I can say 68% of my samples are going to fall between 75 minus one standard deviation and 75 plus one standard deviation. Now, if you go two standard deviations, you get 95% of everything. That's the standard that's usually used. Use two standard deviations in either direction. And what that gets you is two things. One is that 95% of everything is in this area. Two, 5% are the outliers. So 5% of your data is considered to be an outlier, meaning that's like flipping your coin 1,000 times and getting 250 heads. How likely is a fair coin going to be 25 out of 100 times heads? That's absurd. There's no way I would flip a coin 10 times and get two heads and you to say that it's a fair coin. It's possible, but that's in the probably less than 5% of outliers. But that's an example of an outlier. I could flip a coin 10 times and it could be 0 heads. It's possible, but what's the likelihood? It's not much. It's 1 over 2 to the 10th. So that's like way over here. So just like I was saying, you take the mean and you put a standard deviation area around it, and you're starting to get chunks of the population. So if I go 2 standard deviations out, I get 95%. That's the standard. If I go 3, I get, what is that, 99.7%? Usually that becomes too computationally intensive, and 95 is good enough. There's a reason I keep saying it's the standard. So this, I suppose before I move on to margin of error, any questions about this stuff so far? So does that mean it makes sense to everybody? Let me at least get this. How many people does this make sense to? Apparently 0. So that's tough. Yeah, there's 1. At least 1 person is not asleep. That's good. Somewhat. Okay, so that's I can work with that. If it somewhat makes sense, 2 questions. 1, what's stopping it from making total sense? And 2, when I asked, does this make total sense? Why didn't you say anything? Because believe it or not, when I ask you a question, I honestly mean it. I'm not here just to, I don't know, hear myself talk. So which part of this isn't tracking? Let me briefly summarize while, oh, well, if you could get it on your own, like even with a textbook, if you could get it on your own, you would be exceptionally bright. If you could get it on your own without a textbook, you'd be a literal genius. I mean, that means you invented it. That's like Isaac Newton levels of, no one expects that. So the basic gist of what's going on here, I'm curious about how this applies to homework question 1. I wouldn't do that. I definitely don't advise that. Now, again, people are different, so take this with a grain of salt, but my approach has always been focus on the problem at hand and try to see it when, at least when it comes to a lecture. Am I understanding the current concept of what's being talked about? I'll care about what it applies to later. Currently, the concept is this. I'll try to summarize it as best I can. When you've got a population that you can randomly sample, now what the heck does that mean? Population is a group of stuff, and randomly sample means I can close my eyes and take a group of it and assume that it's sufficiently random. So if I can do those 2 things, the following is going to happen. There's going to be an average. There's going to be a true average. I don't know what it is, but it exists and it's somewhere. And 68% of every time I close my eyes and reach into the bag, it's going to be in this range of the average plus or minus a standard deviation. So that standard deviation might be large, it might be small, I don't know. So to put some numbers to it, in our soccer example, I know my mean is 75. I know the true mean is 75%, and I know the standard deviation is, I don't remember what it is. Let's call it like 1. So I know 68% of the time I close my eyes, I'm going to get somewhere between 74 and 76. Okay. I also know 95% of the time. Is it always 68%? Yes. Yes, it is. Because in a normal distribution, a standard deviation to the left and a standard deviation to the right is 68%. The derivation for that would be in the math class. And it will always be 2 to either direction is 95%. So if I use the global standard of 2 standard deviations, what I'm saying is, if this is a life or death, put my hand in the bag, and there's either draw out, you die. If I'm playing Russian roulette, say it that way, a 95% is considered to be good enough. I mean, I still wouldn't want to play it, but if I had to, good enough. So if I've got a Russian roulette where 95% of the time I don't die, it's pretty good. Now here's the problem. Well, I wouldn't say it's a problem, but here's something to understand. This model that I've put to my Russian roulette machine, let's even take it closer. Let's say I have a coin. Tails, I live. Heads, I live. Tails, I die. And I've calculated that the coin comes down heads 95% of the time. Well, I've calculated that, but I could be wrong. How do I know I can be wrong? Well, there's this idea of margin of error. So what the heck is margin of error? It's the likelihood that I made either one or two errors. You don't really need to know what kind they are right now. I think there's another lab on that. So the formula for it is here. I know that's not going to be super interesting. So let's look at the following. So if I have chosen a value, my alpha, now alpha tells me when I'm gonna reject my hypothesis. So if I draw a thing out of the bag and I get a value outside the alpha, I'm going to say, no, my assumption's wrong. So if my alpha is small, meaning the number of times I reject is small, then my margin of error could be big. But if my alpha is large, there's less room for margin of error. So what does this mean? It means that if I choose my alpha to be less likely, then the likelihood of me making a mistake goes up. It's not really that big of a surprise, really. If I choose just one standard deviation, 68%, that means there's less space for me to make an error. If I choose 95%, it means there's more space for me to make an error. Now, calculating margin of error, we'll get into that later. Just need to know that it exists. Okay, we got 5 minutes left. So let's go ahead and try to get through the rest of this. Okay. So this is our one from before, where we did the soccer example. So if I were to take a sample and get 73% of people like soccer, we can say that we are 95% confident that the real percentage is between 70% and 76%. This is what's called the confidence interval. So you have our mean, and you go in either direction by our two standard deviations, which is 3 in this case. It was 1.5, not 1, my bad. And so I'm going to say 95% of the time, that's what our confidence interval is. Well, I guess that's not true. We have a 95% confidence interval is what we have. Okay, let's look at another example. So from a normally distributed population, this part's important because all the stuff we've just talked about only applies to the normal distribution. Every distribution has numbers like the 68% and 95%. It's just that they're different. They're not exactly 68 and 95. But we got a normal one. We're going to randomly take 500 students, and we know the mean of the score on the math section of the SAT was 461. Suppose the standard deviation is 100. We want to estimate the true population for 95% confidence interval. Okay, let's do that. Step one, we're going to get our data. We got 500 students. We got the mean. We want a 95% confidence. We're assuming our standard deviation is 100. And we've got our z-value. How do we get the z-value? There's a formula to calculate it. You just plug all these things in, and there you go. Note that this value, and this value I know. This one we're assuming. Okay. All right, we're going to calculate our margin of error from our formula right here. And we're going to, and the margin of error is equal to this, 8.76. So we want to find the true population mean for our 95% confidence interval. All we have to do is take our X bar, which was our mean, because it's X bar. That's what that literally means. X is our random variable, and bar means mean. It means mean. So we're going to take our mean and go one margin to either side. So we're saying that the true mean, not the one we just calculated, not the one we guessed, we're going to say with 95% confidence, that's between 452 and 469. And that confidence is 95%. Now I can change this. Well, I wouldn't know the exact Z value, but I could change this to be whatever confidence I like. I can make it 68% if I want, but 95 is the standard. Okay, I do see that it is 950 due to having to go through this one first, and almost everybody's left. So what I'll do is I'll look at the homework and go through what we need to do for the recording's sake. So the exercise 1 is what we just did. The 95% confidence interval is what I just did 45 seconds ago. In order for me to calculate the 90% confidence interval on the 99, it's all pretty much exactly the same thing with one important change. The exercise in the lab is the same as homework question 1. Yeah, wait. Oh, yeah, it is. That is the case for quite a few of these. Like this one here, example 3, was from last session's lab. And this question here is the same one that's in the homework. So I'm going to go through how you would calculate them. Everything is exactly the same as far as doing this and doing this. The only thing you need to change is all the stuff that's here. So how does n change? Well, my sample size is 200. Okay, it's going to be 200. What's the mean? Well, I don't know. What am I measuring? I'm measuring the weight. What's the mean weight? 70. So I would, okay, I'll just go ahead and do it. 200 and then 70. What confidence interval do we want? Well, I want 95, 90, and 99. Okay, cool. Let's say I want to do the 90. What's the standard deviation? Well, it's 20. So the question is, can I just hit go? Am I done? The answer to that would be no, because we need to calculate our Z value. So the Z value we have down there, I'm trying to find the formula. The Z value we have right here is for the 95% confidence interval. So this will only work for 0.95. We need to get the Z value associated with 90%. If we want to do the 90% confidence interval. But let's do the 95 real quick. So there's that. And there we go. So 95, I can say with confidence 95% that the true mean of the weight of the dogs is 67.2 to 72.7, somewhere in there. Okay. So that's what's on the homework. This one is another A/B test, which is the exact same thing we did in lab 22. And that'll be that. Today's Friday, right? So I won't have office hours until Tuesday, but you can always email me. Okie dokie then. Everyone have a nice weekend.